All right, welcome everyone to Unit 2. We finished off Unit 1 where we talked about really important tips and tools that we use in science, including scientific method, scientific notation, all that good stuff, but we really haven't gotten into like any chemistry yet. So this is what we're going to talk about in this unit. Unit 2 is all about the intro to chemistry, talking about atoms and the periodic table, which is the title for Unit 2. And specifically for Notes 1 today, we are going to talk about the atomic models. And I'm going to show you really quick where the video for in Canvas can be found with the notes. So in Canvas, you'll see that Notes 1 can be found actually right here, Notes 1 Atoms. And this video will be published right here under this blue link, Notes 1. There's only one assignment for this first section of notes, really easy, but then after that we've got Notes 2, which is pretty long, and then Notes 3 and Notes 4. I will say that this is one of the most extensive units that we will go through in the whole year, not just this semester, but the whole year. Unit 2 is a pretty big one, so we want to make sure that we're catching up with all of our turned-in assignments. We know how to work with Canvas, and we are really staying on track and staying focused. This is the unit that students will begin to notice a increase in difficulty and perhaps really big challenges. Historically, I don't want to scare anyone. Historically, the Unit 2 test is one of the lowest scoring tests, just because maybe kids don't take my warning seriously. I want everyone to really be engaged and stay focused in terms of watching this video and taking the notes. So make sure you are staying engaged in class, paying attention, that good stuff. It's not really difficult material, it's just that there's a lot of it and you got to keep it organized. So we're going to go ahead and get started with Notes 1 on atomic models. So to start off this unit, we're going to discuss some new terms, element, compound, and mixture, and kind of distinguish between those three. There'll be important terms going forward, so we really want to know what those are. But before we get to that, I kind of want to talk about maybe a question that you've had possibly one time in your life, maybe multiple times. I know from personal experience, when I was a little kid, I would think to myself, how small can you break something until it's no longer that thing, right? So if I take like a rock and I break that rock into two pieces, well, now I have two smaller rocks. And then if I take one of those smaller rocks and break it in half again, I have two even smaller rocks. And so the question is, how small can an object be until it loses its properties, until it's no longer a rock, right? Now this applies to literally everything. How small can something be until it loses its properties? Well, that's where we come up with the term element. Elements are things that are pure. They are things that at the smallest scale, they will have the properties of that material. For example, gold, like here's a big chunk of gold, for instance, but obviously you can have small atoms of gold, and those are pure elements. All right, and so when we take these elements that are pure and we mix them with one another, that's when we start to get compounds. All right, so for example, what we see on the screen here is water, and the formula for water, a lot of people already know, is H2O. And what that stands for is that you've got two hydrogen molecules like you see here, 1, 2. So these gray blobs are representing the H, hydrogen, and that's where the H2 comes in. The 2 represents that there's two of them. And then the O is for the oxygen, this one. If I take 2 parts of hydrogen, 1 part oxygen, mix them correctly, you can get water. Okay, so water is a pure compound. You can find it pretty much everywhere on Earth. 70% of our Earth is covered in water. So it's a very common compound. Now, what's the difference between a compound and a mixture? You might think, okay, if I take several elements and mix them together, well, then I have a mixture. Well, not really, because a mixture is a mix of different compounds, not a mix of different elements. Okay, so it's a mix of different compounds. For example, salt water has 2 different things inside, salt and water. Same thing with chocolate milk. It's basically milk and chocolate. And technically in a mixture, you can do chemical or mechanical processes to separate those things. You can take salt water and separate the salt from the water. There's reverse osmosis, or even just boiling the water off. You can separate the salt from the water out. So you can take a mixture and separate the compounds. However, breaking apart a compound is much more difficult. So that's the main difference between a mixture and a compound. Going forward, taking a look at the term element, these are all of the elements that we currently know of. This is the periodic table of elements. I'm sure you've seen it before, possibly in a science textbook, or maybe sometimes a teacher will have a giant poster of the periodic table. And it's color coded for a reason, because different elements have different properties and they'll do different things. And so elements that are like these red ones over here, they'll have similar properties and they'll behave similarly. And same thing with like these orange ones, the ones in the blue, they all kind of behave similarly. So we'll learn more about that later, like the different properties of all these different families of elements. But right now there are currently 118 of these elements. The last one right here, organocin, is the last one that we have discovered so far. So a lot of different elements, they all have different properties. Some have properties that are similar to another element, but these are all unique elements. All right, so let's take a look at examples of two different elements. For instance, we have copper and we have carbon. And copper has properties about it that makes it useful. Like, why do we use it for electricity? Because it's really good at transferring electricity. Why do we use it as coins? Well, it's shiny, it lasts a while, so it's a hard metal. That's another property of copper that we take advantage of, and we use it for specific reasons. Now, for carbon, carbon can be actually found in multiple states, and we'll talk about that later in a different section of notes. But carbon can also be made into diamonds. So diamonds that you use for jewelry or for sometimes for construction material, we actually have saw blades that have diamonds on the outside of the saw, because diamonds are really hard. And that's a property of diamonds, is that they're very, very hard. It's the hardest substance on this planet. Nothing can really scratch a diamond, and nothing can really cut a diamond except for another diamond. So that's what makes it useful for cutting, for like construction equipment. But we also use it for like cutting of other gems. And diamonds are actually really shiny and sparkly, so we use that property for jewelry purposes. Moving forward, we actually can define the word compounds now, and the definition that we have is a substance made up of atoms of two or more different elements joined by chemical bonds. The main word I want to focus on here is different elements. It has to be different elements in order for it to be a compound. You cannot take elements and combine them together of the same type and then call it a compound. For instance, this first example where we have two chlorines, Cl is chlorine. There's one here and there's one here, and we combine them together. That is not a compound. That is actually called a molecule. And a molecule is a group of atoms that are held together by chemical forces. Now, compounds can be molecules, but not all molecules are compounds. So it's kind of tricky. It's kind of like that square rectangle thing, right? Every square is a rectangle, but not every rectangle is a square. Similarly here, every compound is a molecule, but not every molecule is a compound. So these are all molecules that you see on the page here on the slide. These are all molecules, but they are not all compounds, because they are not all they don't all contain different elements. So going for over all of these, we're going to take a look. Cl, this first one, there's two of them. I already talked about that. That is not a compound. That is a molecule, however, of chlorine. Over here we've got phosphorus, 4 different atoms of phosphorus joined together. That again is not a compound. It's a molecule. It's a phosphorus molecule. Over here we've got 2 oxygens bound together. So oxygen is always found in pairs like that. Again, not a compound, but it is a molecule. These molecules down here, these are all compounds. A water molecule has oxygen and hydrogen. A carbon dioxide molecule has carbon and oxygen. And then ammonia has nitrogen and hydrogen. So these are all different elements that have different names and properties. And when you combine them together with other elements, then you're forming compounds. Right? So a mixture, to define that, is a combination of 2 or more substances that can be easily separated through either mechanical means, like boiling or cooking something off, or chemical means. All right. So here's our first practice problem that we see here, and I would like for you to take a moment and classify each of the following as either an element or a compound. So simply write down the letter E or C. So take about, let's say, 2 minutes. Go through all of these and try your best. We'll pause the video right here and then go over the answers. Alright, going over these answers, taking a look at them one at a time, going from left column first and then the right column after that. So sulfur, S8. Let's say you have a molecule of sulfur and there's 8 of them. That is actually just an element, so there's no compounds here because that's the only element present. It's sulfur. Carbon monoxide, we've got a capital C and a capital O, not to confuse you with cobalt, which has a capital C and a lowercase o. This is actually a compound because we have two separate different elements. Okay, so how do you differentiate between like this capital C and capital O versus capital C and lowercase o? Like, what's the difference between these two? Anytime you have a capital letter, that notes the beginning of a new element. So keep that in mind. Anytime we have a capital letter, that's a new element. Okay, sometimes, however, you throw in a lowercase letter because, for instance, C was already taken for carbon, so you can't have cobalt also be C. Cobalt has to be CO, or a chlorine has to be Cl. So you have to give different element abbreviations to the names because you can't repeat them, of course. So cobalt, in this case, is an element. Potassium is going to be also an element. There's only one element here. Iron, which is Fe, is going to be an element. Methane, CH4, this is a compound because we have carbon and hydrogen. Calcium, C, and then lowercase a, that is an element. Sodium chloride, NaCl, that is a compound. Oxygen, O2, is an element. And carbonic acid, H2CO3, that is also a compound. All right, you don't necessarily need to know what any of these things are, obviously, but right now we're just trying to identify the symbols and whether or not they're a compound or not. Okay, so let's talk about the atomic model of chemistry. Like, where did atoms come from? Where did we get this idea or this picture of an atom and the evolution of that? And we're going to start with this guy from a long time ago. He is a Greek guy by the name of Democritus. And around 450 BC, so about 2,500 years ago, give or take, he came up with this idea that matter was made up of small particles called atoms. And basically, he was answering the question that I had in the beginning of this lecture, which is, how small can you break something apart until it loses the properties of that thing? How small can something be? And so he came up with this idea of atoms, but the Greek word that he came up with was atomos, A-T-O-M-O-S. Okay, so atomos was the word that he came up with, and basically that means something that cannot be broken further apart, and that's where we get the word atoms from. It's from the Greek word atomos. All right, so that's Democritus, and he didn't really do any scientific experiments. He was kind of more of like a philosopher. He was technically a scientist in his time, but they're limited by the capacity of what he could do, lack of technology and things like that, of course. So basically he just said, okay, little small marbles or particles, those are called atoms. Moving forward, though, it wasn't until like 2,500 years later, basically, John Dalton in 1807, he came up with this idea that atoms existed as small spheres. So he said, yes, atoms are really, really, really small things, just like how Democritus said, but they exist as spheres. And he also stated that atoms of a specific element are exactly alike. So what that means is, if I were to take a sample of oxygen on this part of the planet and go to this part, the other part of the planet, and take a sample of oxygen, I would not be able to tell those apart. Okay? So, for instance, if scientists are looking for water on different planets, or like the moon, for instance, if we're going to Mars to look for water, we are looking for 2 parts of hydrogen and 1 part of oxygen, because John Dalton's point here that all atoms of a specific element are exactly alike holds true. Oxygen is oxygen everywhere. It's always going to be the same. Same thing with hydrogen, same thing with any other element. They're always going to be the same. The other point that he made up is that, yes, atoms exist as spheres, but we can combine those spheres together to form different compounds. Going back to Democritus really quick, Democritus didn't think of different types of elements. He knew everything was made of small atoms, but he kind of thought everything was made up of the same 5 things: water, air, earth, fire, and something called ether, which gives things life. Okay, so he said everything is made up of those things, and that humans were just a mixture of, earth and water and all this other stuff, and with ether we've given it life. Okay, so Democritus didn't really understand the concept of elements. That was not until John Dalton, right? And this is one of those experiments that John Dalton did. He took 2 parts of hydrogen, maybe not necessarily in balloons, but he collected 2 parts of hydrogen, 1 part of oxygen, And if you know a little bit of chemistry here, if you mix hydrogen and oxygen together, that actually is a very dangerous mixture of gases, because if you light it on fire, it's extremely explosive. If you've ever seen the movie The Martian with Matt Damon, there's like a scene where he's actually making water inside of his little habitat on Mars, and he does that by mixing hydrogen with oxygen, and he burns it, and then he actually creates a very small explosion at one point. Okay, so that's how you make water, and this is what's called the law of definite proportions. Okay, so we know the formula for water is H2O, and that is because we have exactly 2 parts of hydrogen and 1 part of oxygen. You can't throw in a third part of hydrogen and then expect it to end up inside of the water. It's not H3O, right? It's H2O. It's always going to be like that. So the definite proportions means that whatever you put in is whatever you get out. Just like if you were, let's say, baking a cake. If you baked a cake and you had 2 cups of flour, 1 cup of sugar, a stick of butter, and like 4 eggs, and then you end up eating the entire cake, technically you ate 2 cups of flour, 1 cup of sugar, a whole stick of butter, and 4 eggs. So you ate all of that. Maybe not separately, of course, but technically with the law of definite proportions, that is the equivalent. All right, so that was John Dalton. A couple of years later, so John Dalton, that was back in 1807. So about 100 years later, just shy, 97 years later, John Thomson took that idea of the atoms and the elements that John Dalton came up with, and he did this experiment where he basically put a gas inside of a glass tube, and he sealed off the ends. And then at the ends of the glass tube, he attached pieces of little metal here. So he's got a piece of metal right there where my laser's pointing, and then another piece of metal right here. And those pieces of metal are actually making contact with the glass that's sealed inside this tube. And this is called the cathode ray tube experiment. And what he did is he hooked up these pieces of metal to a voltage source, like a battery. And what he observed is, okay, there's like a weird light going all the way through, straight across. And you can actually see a picture of here. This is the exact same experiment that he did. He had a tube filled with a specific gas. He applied electricity to it. And when he did, he saw a beam of light going all the way across. He thought that was pretty cool, and it was an interesting find. Wrote down what he thought about it. But then the other thing he found is that if he held up a magnet, he could actually steer this beam of light. So in the second picture here, you can see this person is holding a magnet right there, and they are skewing this beam away from this anode part with this other piece of metal. Okay, and I can actually show you a video of that here. We're going to take a look at this video of someone doing that. So you can see here someone is simply moving the beam of light with a magnet. And so John Thomson thought this was very interesting, and he said, well, the only way this is really possible is if the particles, the elements themselves, are made up of different parts, like positive parts and negative parts, okay? Because electricity has a positive and negative part, and if I can steer that around with a magnet, then the particles themselves inside the tube, inside this gas, they also have to be made up of positives and negatives, okay? So he went on with this idea, and then just on a side note, cathode ray tubes was a technology that was later used in the really big box TVs, but this technology is pretty much outdated now, and you can't even like find these things in donation stores anymore because no one wants to accept them. They're just really big and heavy, and the technology is outdated. So going on though, we're going to continue talking about John Thomson's discovery. So remember what I said earlier? I said that he discovered that inside the atoms there are positive and negative portions. So he thought of a kind of like a model of this. He was kind of thinking, okay, what does that look like? What do these atoms, these spheres, look like? Well, he said that the atom itself was like a big ball of positive goop. Okay, it's just like a positive charge. And then embedded inside of that were electrons, kind of like a 3D view. I know this is kind of like a bad picture because this is a 2D representation and not really a 3D representation. And he came up with this idea of what's called the plum pudding model, right? And plum pudding back in the day was not like what you would think of plum pudding. Pudding for us is like, you know, very runny, but in old times like this, a plum pudding would be more of like a biscuit. So think of this model of like maybe like a chocolate chip muffin. Okay, you got the muffin, and if the muffin is actually like a sphere instead of a muffin shape, then the bread part of the muffin, according to John Thomson's model, would be the positive portion. It'd be the plus. The minus, the electrons, are going to be the chocolate chips that are embedded throughout the muffin. And so this is kind of like with the plum pudding model. So instead of a chocolate chips inside of like this biscuit thing, it's little tiny bits of plum. So that's John Thomson's model back in 1904. All right, so a few years later in 1911, this guy with a very fancy name, Ernest Rutherford, was doing more experiments with chemistry. Right now, at this point in 1911, it's pretty much accepted that there are atoms that are spheres, and they have a positive region and a negative region. And right now, we are accepting the plum pudding model that the spheres are going to be the positive, bread portion if we're comparing it to the chocolate chip muffin or the plum pudding model, and then the electrons are going to be embedded all throughout. So Ernest Rutherford then did this crazy experiment where he took a source of radioactive material and he put it inside of a lead box. If you know anything about lead, you know that it's a material that's often used to prevent radiation because it's very heavy and thick. Sometimes, like if you go to the dentist office and you're getting like a x-ray of your teeth, they put this giant lead vest on top of you and it's very heavy, and that's to prevent radiation going through. So he had this cube of lead, and he had a way of opening this cube, and he put a piece of radioactive material inside of it. Now, this cube did have an opening. There was an opening, like a little tiny opening right here, like just a small dot, and the radiation was actually able to come out like a beam. Okay, so it came out like a beam of light, almost like a radiation. And then what he did, what Ernest Rutherford did, is put up a sheet of gold foil. It's a very sophisticated experiment here. The gold foil is extremely thin. If you've ever dealt with a gold foil, you can buy it for like art purposes. Sometimes even like bakers will put on cake or whatever because you can technically eat it. Gold foil is a really, really, really thin. You can just basically blow on it and it will rip. So he somehow got a sheet of gold foil and was able to shoot the beam of light straight into the gold foil, and he wanted to observe what happened. So he was able to put this giant ring around the gold foil. So he's got this giant ring. There's a gap here, obviously, so that the beam of light can go through. And what he noticed is that some of the beam bounced off in different angles, which is what he expected. Some of it bounced right back to the source, also what he expected. But then he found somehow that the beam of light was going through the foil and bouncing off in different directions. And he found this to be really, really interesting because the only way that that would be possible is if the model of the atom looked like this. He wanted to kind of prove or disprove John Thomson's model. John Thomson's model, again, is this plum pudding. And if that beam of light called alpha particles went through John Thomson's model, what would have happened is that it would have gone through the entire thing. But that's not what happened. Instead, what happened is that some of the beams got deflected, right? So if a beam of light hits this central part, it gets deflected off this way. If it hits this region, it gets deflected off this way. And they just kind of go in all sorts of directions. And so if we take a look at this beam of light once more, there are atoms of gold inside of this gold foil, obviously. And those atoms of gold have regions in the middle where it is really, really concentrated and very dense. And it's actually dense enough where it can deflect the beam of alpha particles away. And so Ernest Rutherford came up with a name for this region, and this region is called the nucleus. The nucleus is the region in the center where we contain the protons. The proton is no longer this bread plum pudding model that we had. That model is now outdated. Now what we have is a region in the middle called the nucleus, and that's where the protons are. Later on, we'll discover that there are something called neutrons, but that's not until later. But for right now, we know there are protons in the center. Where are the electrons then if the protons are in the center? Well, Ernest Rutherford thought about that, and he said, well, so the protons are in the center. The outside has to contain the electrons. They're just kind of spinning around the nucleus, going around in circles really, really fast at the speed of light. That's how fast they're going. You've probably seen this model of the atom before. maybe like on a TV show or somewhere like in a science catalog, just to depict what the atoms look like. This is actually an incorrect model of what the atom looks like. We don't accept this model anymore. But at the time, Rutherford's atom was the best model that we have. Here are the details. This is what's called the planetary model. You have your nucleus in the center. There are things called protons and there are things called neutrons, which we'll talk about later. And they contain almost all of the mass, like 99.999% of the mass. More than that is going to be contained here in the nucleus. And this is going to be positively charged. So you got your plus sign here, positively charged in the center. The electrons are going to be negative and they're going to be spinning around here. Okay? And so that's Rutherford's model. A couple of years later, we come up with Niels Bohr's model. Niels Bohr's came out with a model 2 years after Ernest Rutherford. And Niels Bohr's model looks like this. And the main difference you'll see is that the pathways that the electrons follow, they no longer intersect. So if we go back here, those pathways they look like they're intersecting, and that's actually not true anymore with Niels Bohr's model. This is called the orbital model. And so some adjustments were made to Rutherford's model. Everything that Rutherford did with the gold foil experiment was accepted, except for that last drawing they came up with. So Niels Bohr came up with this model where electrons orbited planets around kind of like the sun. And this indicated that the electrons orbit in different energy levels. Okay, so the closer you were to the nucleus, the lower your energy level. And the further away you were from the nucleus, the higher your energy as an electron. All right, but this model, however, restricts electrons to certain orbits and cannot model every element. So that was the big downfall of this model. Okay, so the electrons, they are no longer like in those intersecting paths. They are stuck on their energy levels going around in circles. All right, so just to recap, here's kind of like this graphic organizer of the history of the atom. So a long time ago, Democritus came up with this idea of atomos, which is the smallest particles. He didn't necessarily establish that they were spheres, but I just put it up there as a sphere. That wasn't until John Thomson. And John Thomson also came up with the idea, here's the big thing, that smaller subatomic particles exist. And so he came up with the idea of protons and neutrons. Then we had Ernest Rutherford just a couple of years later, like I think 7 years later, who came up with the idea of protons are in the center, called the nucleus, so he established that term, and the electrons are spinning around. And then finally, 2 years after Ernest Rutherford, Niels Bohr came up with this idea that electrons aren't just spinning randomly, they have energy levels. They are on specific things called orbitals. All right, so if you want to maybe jot this down, you can make a copy of this graphic organizer yourself. I'm going to go ahead and hide here, and you can pause the video if you'd like, just to make your own version of this. All right, so we're going to move forward now. So this is just basically a brief history of like the shape of the atom and how we got to it. But what we know now is that none of those models are actually true. So I'm going to show you what we accept as of today. Electron cloud model, which has been in the works since basically 1926, so almost 100 years, we've accepted this model of the atom. And I mean, who's to say that in the future we'll find out more that will kind of change the shape of the atom, but we're pretty certain that this is what the shape of the atom looks like. A lot of research was done with the atom, especially around the time of World War II, the Manhattan Project and Oppenheimer and all of that. So the electron cloud model is what we accept to be today, where basically you still have a nucleus, just like how Niels Bohr and Ernest Rutherford, those two guys, have been saying. But now you've got like this cloud on the outside, still kind of holding on to that idea of orbitals that Niels Bohr had, except now we have this idea that the atoms or the electrons can actually jump from one orbital to another. So let me go back to that one picture that we had. So in Niels Bohr's model right here on the bottom right, we are taking a look that these green electrons, they're not leaving their orbitals, but what we know is that they can actually hop from one orbital to the next. They can change their energy level just as long as that they find a replacement, like maybe two electrons swap places. And so when they do this really fast, they do this at the speed of light, it's blurry because you can't really see what's happening. So when they do that, it kind of forms like what is known as like cloud. So you have a cloud of electrons that are moving really fast at the speed of light, and this is what's called the electron cloud model. All right, and this is what we accept today. This is a picture of a cloud model, and the exact location of the electron cannot be determined just because it's moving at the speed of light. It's going very, very fast. But the best pictures that we have gotten have all shown that this cloud model is supported. This is an actual picture that we have of a large atom, and the darker the shading, the better chance of finding an electron there. So that's where that cloud is. That's the orbital, right? And you can see here there's a very clear region where it's very dark, and then it's not like a clear cutoff. It just kind of fades out. You can still find electrons like down here along the edge, but the darker the region, the more likely it is you'll find an electron there. Okay, so that's called the electron cloud model, and that's what we accept today. All right, so right now what we're going to do is go over practice problems 1 through 4. I'd like for you to pause the video and take 3 minutes to work on those right now. All right, so number 1 says, which of Dalton's statements about the atom was proven false by J.J. Thomson? A. Atoms cannot be subdivided. B. Atoms are tiny. C. Atoms of different elements are not identical. Or D. Atoms join to form molecules. Well, if you remember, J.J. Thomson, or John Thomson, was the one that came up with the plum pudding model. So he's the one that kind of discovered a proton region and an electron region. So he actually was able to subdivide the atoms. So A is the correct answer choice here. Atoms cannot be subdivided. That was proven false by John Thomson. Number 2 says, what did Rutherford learn about the atom from the gold foil experiment? A. Atoms have electrons. B. Atoms have a nucleus. C. Atoms have a negative charge embedded in the sphere of positive charge. Or D. The nucleus is most of the atom's volume. What he actually learned is that atoms have a nucleus. So we talked about how that alpha particle beam was being deflected by a very dense region in the center, and so he kind of named that the nucleus, the center of the atom. Number 3, which statement is not true of Bohr's model of the atom? Electrons cannot be between energy levels, electrons orbit the nucleus, an electron's path is not known exactly, or electrons exist in energy levels. Niels Bohr's model is not true in the sense that electrons cannot be between energy levels. They can and often are in between energy levels. They kind of hop between the two. So they kind of form that cloud. And then number 4, what subatomic particle can be found in regions called orbitals? Protons, neutrons, electrons, or photons? The correct answer here is electrons. All right, so that concludes Notes 1 on the atomic model.